Yeah, this is what we were talking in the last class. We were talking about lagging and leading conditions. Comparing two waveforms. We usually take, when you have a voltage and current source as signals, we definitely take voltage as reference. And comparing with voltage, we will say whether the current is leading or lagging in the system. So we have gone through new various examples where we can see leading, lagging. Fine. So today we will be discussing about some definitions related to AC quantities such as instantaneous values, RMS values, average values, and so on. Fine. So by definition, what do you mean by instantaneous value? We were talking about this instantaneous value in the last class, where we can define the instantaneous value in general terms as that is the magnitude of the signal, which at any particular instant of time. So the basic definition given for instantaneous value is the instantaneous value of AC signal is the value of voltage or current at any particular at specified instant of time, right? The value may be 0 if the particular instant is the time in the cycle at which polarity of the voltage is changing. That's what does it mean? The polarity is changing. It might be at some zero crossings, right? We know that at these zero crossings, the value of voltage or a current will be equal to 0, right? If you are asking for instantaneous value at such instants, right? At so now when so if you consider the instantaneous value at the peak, it might at this instant it might be something, it will give the peak value, right? So instantaneous value will not be a constant value, it will be varying with respect to the time or with respect to the instant when we are measuring it or when we are seeing it, right? So the instantaneous value of AC quantity is the value of voltage or current at any one particular instant, right? And there are actually a infinite number of instantaneous values before 0 and the peak value, right? In between 0 and peak value, we have many infinite number of instantaneous values you can take, right? So coming to the next, average value. So this is one of the fundamental and important values of AC quantity. So in general, when you consider the AC waveform or a DC waveform, what are the elements you have in a DC? Generally, we represent DC usually. Suppose if this is a voltage for a DC in a DC circuit, we generally define this magnitude as VDC. That will be fine, right? Suppose it has certain magnitude, it remains constant. So let me say first, say that the voltage is VDC is equal to 10 volts. But when it comes for AC or alternating waveform, we can't represent this. We can represent them in 3 different terms. One is a maximum voltage, and second one is a RMS voltage, and third one is a average value. Right. So out of these 3, these are the types of representation in AC. Right. Since it's a time varying quantity, we can represent either with a maximum value or a RMS value or a average value. And we are talking about average value now. So what is the definition for the average value? What do you mean by average value? The average value of AC current of an AC current or voltage is the average of all the instantaneous values during one alternation. Alternation, what does it mean by alternation? Is a half cycle. What does this alternation mean? Alternation means a half cycle. We know that two complete half cycles, two half cycle. What do you mean by cycle? Is a combination of two half cycles. What are the two half cycles you can generally combine? Is a positive half cycle and a negative half cycle. So each of that half cycle you call it as an alternation, right? So the average value of an AC current or a voltage is calculated over a half cycle. Why don't we calculate it for a full cycle? Is that the yeah. So since we have a if I consider a pure sinusoidal waveform, but what you are talking is about what's the need for why we are considering why do we calculate average value only for half cycle is that since we know that if it is a pure sinusoidal waveform, you have a positive waveform and a negative cycle, positive half cycle and a negative half cycle, and both of them are, if they are identical, definitely the value average value will become, it will become zero. So that's the reason why we go for using only doing the calculations only for first half cycle, that is only for positive cycle or the negative cycle, right? So what does it mean is the average value of an AC current or a voltage is the average of all the instantaneous value during one half cycle. Since the voltage increases from 0 to peak value and decreases back to 0 during one alteration, the average value must lie between those two limits. Suppose say if this is a sinusoidal waveform, right? See here from the value of the voltage, if this is a voltage waveform, right? The value of voltage waveform starts from 0, goes to maximum peak and comes back to 0. So if I do some average for calculation for this, it will be something between these two limits based on the depth of this signal, based on the waveform shape of the waveform. It may take any of these value in between. If this is a sinusoidal, this some value you may get average value somewhere in between maximum and minimum values, right? So it is it is possible to determine the average value by adding together a series of instantaneous values of alteration between 0 and 180 degrees and then dividing the sum by number of instantaneous values used. So we can how do you get to this value? If you want to get a constant average value, how can you calculate it? Take this positive half, divide this into sections, various values of instants, and see, I have divided this waveform from 0 to 180 into 6 segments, 1, 2, 3, 4, 5, 6. So consider these other two as well, right? So now if I can divide this into 7 levels, 7 instants, the value of voltage or value of the quantity at these particular instants, I can take them and do an average for these, right? Sum of all these values, that is sum of all the values which you have here, values divided by the number of values, that is based on the number, right? How many instants we are taking is 7. So divide them with this value, get the average, right? For a pure sinusoidal waveform, the average value is equal to 0.636 times the peak value. So in general, we generally denote this V average value for a sinusoidal waveform as 0.637 or 636 V maximum, right? So since it's a sinusoidal waveform, it's a pure sinusoidal, right? So even if I take any number of instance of the values and calculate it, we get only 0.637 times of V maximum. And V average can be given as this 0.637 V maximum. That is what the derivation is. You just take the calculation and do it, right? Suppose if you take a sinusoidal waveform, you assume some magnitudes on that, right? Yeah, you will get 2 V maximum by pi. What's the value of resultant of that?
That only, sir. 0.637.
Yeah, both are same, right?
For I naught also we'll get same only
Same,
because they are
same.
in phase.
Yeah, V average, or we will do the same calculation for I
Same
average.
no, sir. I naught sin omega t or V naught sin omega t. Just
Yeah,
that V and I are changing.
both are same.
Yes.
Yeah, fine. So this is about the average value for a alternating quantity. So similarly, we have one more. We can explain this in terms of this example. See, let this be a sum. And can we calculate the average value for a non-sinusoidal waveform? Yes, we can do it, right? So we can do the same calculation for even for non-sinusoidal waveforms. Suppose if this is a waveform which is alternating in nature, but seems to be uh, doesn't seems to be a pure sinusoidal waveform, right? Suppose if I want to calculate the average value for this, if I want to calculate the average value for this, so we have to do this can be done in this way, where the whole quantity which is available here is derived over this, or else is adjusted to this length, right? So see in the second example, negative exercise, the peak is adjusted to the negative value here. Whenever you do the calculations, we do it for from how did you get 2v maximum pi? Did you integrate it over the
Yes,
0
sir.
to pi?
Integral of 0 to t by 2 V naught sin omega t dt, then by integral of 0 to t by 2 dt.
Yeah. So did you derive it only for half cycle or it for full cycle?
No, sir. For half cycle, no. We are
Yeah.
taking limits from 0 to t
0
by
to
2.
t by 2, right?
T by 2. Yes.
Yeah. So 0 to t by 2, similar things can be done here, right? We can take the average of these two by adjusting up to this specific distance. So this is given in general, but in general, we can do an average up to here. Suppose if it for half cycle, instead of getting a time varying, this is a waveform for instantaneous values, right? So if at all we want to get an average, we can make it to calculate from 0 to as this from 0 to t by 2, or you can directly say it as 0 to pi, right? 0 to pi, I can do the calculation, so I can fill this here up to here, right? Some standard value. So you'll get some value which is uh, in between maximum minimum. That's what the statement mean, right? So ignore these diagrams in the B section because it is a generalized example, right? Now, if I take an example here, plotting speed versus time for an automobile exertion, right? So what is the average speed you are going to get here? Suppose if it is for first 2 hours, the speed was maintained as 60 miles per hour, and from 2 to 2.5 there is no speed, and from 2.5 to 5 the average speed is from 50 miles per hour. What could be the average speed? How do you calculate it in general?
Total distance by total time.
Yeah, total distance by
Total
total
time taken.
time. Yeah, I will give one more example here. See, you have a square wave, right? I have a square wave. Sorry, what's the answer for this? It's 45 miles per hour, right? How do you come to the conclusion? The value which you gain as average. See here, it is coming to our definition. What we have said, it should be between minimum and maximum positions. Maximum is 60, minimum is 0. It is lying at 45 miles per hour. How did you come to that speed conclusion? How can you calculate it? See,
60 plus 50, we can take 60 plus 50 as total distance.
total, no, that's miles per hour, right?
Okay, sir. Okay.
So what should be done now? Multiply them, divide by hours, you will get the average.
A1, A2 by number of hours you're saying,
No,
sir.
60 into 2 plus 2.5
Oh,
into 50 divided by hours. What is the hours you have? 2 plus 2.5.
okay. Understood, sir.
Yeah, average speed. You can get the average speed somewhere here. Now, similarly, let us go for this example because it's more related to us. Fine. So, determine the average value of waveform of figure 1.13.37. This one. So what's the average value of this square wave? This is a square wave, right? So it has moved from 0 to 1 to 2, that is a cycle. The time period for this is 2 milliseconds, right? The magnitude, the peak value is 10 in the positive cycle is 10B and minus 10B. So what's the average value now? Since they are equal in magnitudes, the value of average will be equal to 0, right? Now, what happens to the second case when they are not equal? When they are not equal, one is the positive peak is 14, negative peak is minus 6. So what could be the equivalent average for this? Is 4 volts, right?
Yes, sir.
Yeah. So similarly, we can go for having some average here values. These are just examples where you have 3 for 4 milliseconds and 1 for minus 1 volt for 4 milliseconds. The average will be 1 volt. This is how we do the calculations. And however, the average values, we are not going to calculate the average values for these things. Here is a waveform C equation which you derived, right?
Yes, sir. Same value.
Yeah. So yeah, let us move on to the this is an example where what happens if the average value is calculated for a complete cycle, right? That's the reason we are not doing that. So let us go for the effective value or the RMS value. So what do you mean by effective value, or what do you mean root mean square value? RMS is nothing but root mean square value, right? So this is just an experimental setup to establish a relation between DC and AC quantities. So what does the relation mean? What is that? What is it? What does it indicate? See, I have a AC source, I have a DC source, I have a switch 1, switch 2, and both are given for the same resistor. And let me take this as a thermometer or a temperature measurement device, right? The effective value, as I already said you that the values in AC are average, RMS, and maximum value. Fine. So effective value here, what is the definition for effective value? This is the value of AC signal that will have the same effect on the resistance as comparable values of DC voltage or current, which will have on the same resistance. What does it indicate is, suppose say, if I close switch S1 first, assume that this switch is closed, right? This, assume that this switch is closed, this is open somehow. So what will happen here now? We will allow some amount of IDC to flow through this resistor element for some period of time T, right? So we know that as the current flows for a period of T, definitely it will be resulting as a heat energy. You know, what is the equation for I square RT? What does it you call it as? You call it as a heat energy, right? So if I square RT, if you allow the current I, that is IDC, I can write it as IDC. So IDC square RT. Suppose if I allow some IDC amount of current IDC for a time period of T through this resistor R, it will generate a heat energy of I square or IDC square RT. So what will happen? Let us say that it has produced some heat of some joules, or say it has some represented in terms of watts or kilowatts. Let me write it some value X joules or something. Whatever the units are, you take it as some value X. Now we'll once this heating is done, we'll open the switch and we will allow the water and the resistor to get cooled down. And again, after a day or so, when the things come to normal position, instead of closing switch S1, we'll close switch S2. What are the conditions we are going to take now is that we will ensure that the amount of current that flows in the resistive element should be same as that of IDC, right? And it has to be given for the same amount of time as well. However, the resistor remains same. So the time with the for which the AC has to fed to the resistor should be same as the time that during which the DC was fed, right? If I have fed DC for 5 minutes, I also feed this AC current for 5 minutes. Right? What is the magnitude of current that used to flow here? Then what is the value of current that the ammeter has to measure here? The ammeter which measures here should measure the same value of current equal to IDC. What was the magnitude of IDC which was going? Let me say that this is 5 amperes. The ammeter should also read it as 5 amperes when you feed AC. Now what will happen is, we will see that the temperature measured by this measuring device will give same heat when same heat of X joules, right? When this amount of current flows, it also produces the same value of X joules, where this value of magnitude of this current is something called as RMS value. Neither the average value nor the maximum value will give the same amount of heat. It's only the RMS value which will give the exact heat value that is produced by a DC quantity. So that's the reason why AC quantity, which is comparable with DC, you call it as RMS value, or you call it as effective value, right? So for this reason, the effective value is often called as root mean square value. It is possible to compute the effective value of a sine wave of current to a good degree of accuracy by taking equally spaced instantaneous values of current along the curve and extracting the square root of average of the sum of the squared values. What does it indicate? Suppose if I want to calculate a RMS value for a waveform, how do we calculate it? How did we do for average? Suppose if I have a sinusoidal wave, if I have a waveform, right? How do I calculate it for average? What did I say to do? What did we say to do for this average value? I said that to calculate the value of instantaneous, take the values of instantaneous magnitudes of the instantaneous values and take the instants 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So add the all values, the magnitude at instant 1, magnitude at instant 2, right? V2 up to, you just go to V10 divided by 10. So you'll get some value, you call it as V average. This is what I said, right? Now, if I want to calculate the value of root mean square value, I do the same thing, right?
We whole square the average, sir. Whole
Yeah,
square and then add all the averages and take
yeah,
under.
you just take this, instead of taking a single value, take the square values. That's it. Is that okay?
Yes, sir.
So we can calculate the value of RMS value by taking a root mean square value. That is, take the instants, just divide the waveform into 10 some instants and take the square of the instantaneous values, divide with the number of average number of the instants and take the under root. So this will give the value of root mean square value. So the effective value is also calculated by using this method. So you call it as a RMS value as well. For a pure sinusoidal waveform, the RMS value will be equal to 0.707 times that of maximum value. So once you calculate the value of maximum, you can get the value of RMS as well. So what is the relation you have? 0.707. I think it's 1 by under root 2, right?
Yes, sir. I max by root 2.
Yeah, I max by root 2. So V RMS, or you get as, I can write it here as V RMS is equal to V max by root 2, right?
Yes, sir.
Or we can write in the other sense as V max is equal to root 2 times of V RMS.
Sir, for calculations, mostly we'll use VRMS, no, sir. If they have given
Yeah,
220 volts.
most of the
supply.
time.
Yes,
Yeah,
sir.
yeah, most of the time, or say most in all the cases, until unless specified, whatever the value they are mentioning. If I say 220 volts DC sub, 230 volts single phase AC supply, it implies that it's RMS value. Yeah.
Yes, sir.
Yeah. So most of the times, until unless specified, this will be the values which are given will be RMS value. And most of the things which we measure in your laboratory using some equipment, measuring devices, they also exhibit the same value of RMS. So if I have an ammeter, I think you have used a digital ammeter in your BW lab.
Yes, sir. Yes.
Suppose if it is an indicating instrument, what is the value that it is displaying outside when I will give a AC supply is the RMS value. So most of all the indicating instruments will definitely give the value of RMS values, not the average or the peak values, but they'll give the value of RMS.
But in questions, always voltage they'll give around 220, 230 like that. So we
Yeah,
have to
yeah.
convert.
Yeah, most of the times. What's the need to convert? When you are required to find V maximum, then you need to convert it.
No, sir. Means for calculations, if we are calculating like components are involved, like inductor and all those,
Yeah, yeah, yeah. Wherever,
then we have to.
yeah, wherever the calculation is required and wherever you want that value to be specifically used somewhere in terms of RMS, average, or maximum. So these are the equations we have, right?
Yes.
So we can represent that average value in terms of maximum as what is the equation we wrote? V average is equal to 0.637 V maximum.
637.
Similarly, V RMS you can write it as 0.707 of V maximum. So, won't you get any doubts, sir? Why is what happens if the waveform for a sinusoidal waveform, why it is only 0.637 or 0.707? What
Means,
does
sir.
it will it change if the magnitude changes?
Yes, sir. It is dependent upon V naught, no, sir.
Yeah, but the fundamental structure will be sinusoidal, so definitely the values remain same, right? This magnitude remains same, right?
Yes, sir.
So that's the standard derivation or standard formula used for AC quantities which are having pure sinusoidal waveform, right? V average is equal to 0.67 times of V maximum. Suppose
Sir,
if you know the maximum value, I think we can calculate the value of RMS and average, right?
yes, sir. Because in the derivation part, that sine wave part, it will go off, sir.
Yeah,
We'll only
yeah.
be left with the magnitude
Magnitudes,
and
yeah.
some value like root 2 by root
So that is how
2.
we end up. That is how we end up to calculate the value of effective or RMS values, right? So in general, when it is a AC system, DC system, what is the equation we write for a power? And since we are calling it as effective or RMS value, definitely the value of power will be the RMS value, right? It will not be the average or it will not be the maximum. So the calculation of power will also involve the RMS, right? Suppose if it is a DC system, what is the equation for power we write? VDC or else VDC into IDC, right? VDC into IDC. Suppose if it is a RMS value, AC system, what's the equation we give for power? We have to give it for I square R, where I is equal to be Im sin omega t. And if I substitute that
VRMS into IRMS.
VRMS into IRMS or any equation, right? We can even the same equation we can write for here VRMS into IRMS, right? Or we have a fraction for RMS in terms of maximum. You can use also. You can also
Yes,
use
sir.
that.
We'll get V naught square by 2 then.
Yeah, what not?
V maximum.
Yeah. So I square Im sin omega t whole square into R. So we can expand this square term as this. What is the equation we are going to get if I use a square term? Sin square omega t. What is the value you are going to get? Expanding it. I can write it as 1 by 2, 1 minus cos 2 omega t by 2, right? So once we calculate the value of power, what is the equation we are going to get at the end is this. In DC, it's very simple. VDC into IDC, multiplying the magnitudes, that's fine. But when it comes for AC, it depends on the frequency as well, right? So what's the equation I have? Im square R by 2 minus Im square R by 2 cos 2 omega t. So I can divide this into two terms, right? I can take Im square common, Im square by 2 into R. This has 1 minus cos 2 omega t. So what's the equation we are going to get here? Anyhow, since the value of frequency is involved here, the value becomes 0, right? The only term which is left is Im square R by 2. will represent the power that is dissipated. This is in general. This is in general. Suppose if I want to calculate the power for different applications, say different parameters, say for a resistor, for an inductor, for a capacitor, you follow the same procedure. Instead of using I am sin omega t, if it is an inductor, what is the equation I write here with reference to current voltage? Or we can do the same calculation as we said, right? So what is the equation I can write for PAC in terms of VAC and IAC? I can multiply it with V and I. What is the equation for V? Vm sin omega t. And what is the equation for I? Im sin omega t. I think we get the same equation here. Vm Im sin square omega t, right? So expanding this, what is the equation you are going to get? Vm Im. What is the expansion for sin square omega t? I already have here. What is that? Vm Im by 2, 1 minus cos 2 omega t. Isn't it? So what is the value I am going to get here? Is this value will become 0, right? Cos 2 omega t will become 0. Why?
If when frequency is constant, sir, you are telling?
Not constant. Omega t. Substitute any value of omega t. What will the value of cos? Cos 2 omega t.
I didn't understand, sir.
Yeah.
Once again.
1 second. If say this is the value of waveform and we are writing it as omega t, right?
Yes, sir.
For this, we are calculating the average value for half cycle. Isn't it?
Yes, sir.
0 to pi. Suppose if this is 2 omega t, if this waveform is 2 omega t, what will happen to this waveform? Will the waveform remain same or will it change?
It will become pi by 2, sir, instead of
No,
pi.
instead of pi, it will become something like this, right?
Yes, sir. It will shrink.
So
Yes.
this equation you have 2 omega t. So since we are calculating the average value over a complete from cycle 0 to pi, what is the average value of this frequency signal?
We'll get 0, sir.
This
1
will
minus
become
1.
0,
Yes.
right? So now if I substitute the same thing here, what is the value I am going to get here? What is the equation I am going to get here? It's Vm Im by 2. It's Vm Im by 2 and this value is almost equal to 0. So I have only 1. So what is the expansion I can write for this? Can I write it as Vm by root 2 into Im by root 2?
Yes, sir.
So what is Vm by root 2? Is VRMS. And what is Im by root 2? Is
IRMS.
IRMS. So whenever I want to get AC power, the equation can be written like this in terms of RMS value. No doubt we have followed the same principle where we wrote the equation for DC, right? We are writing the same instantaneous value. What is the instantaneous power we wrote? Small p is equal to small v into small I. Is that okay?
Yes, sir.
Yeah. So this is how you calculate the value of power in AC system. Yeah. So whenever you are asked to calculate the power, you just multiply the instantaneous values in AC and the final steady state values in DC. Right? And this is how you get the values of maximum relation between IDC and how did I relate directly here? IDC is equal to 0.707 of maximum because we assumed that IDC is equal to IRMS, right? We are always assuming that IDC is equal to IRMS, so we directly wrote the value as 707 times of IRMS. Is that okay?
Yes, sir.
Yeah. Let us consider an example, right? So let us consider the behavior of an iron machine as a pure resistive load of 1 kilowatt supplied by a single phase AC voltage of 220 volts 50 hertz for domestic application. The supplied voltage can be represented mathematically as V of t is equal to Vm sin omega t. So what should be done? What is to be done? Let us consider the behavior of iron machine as a pure inductive. The load is 1 kilowatt. Supplied 1 kilowatt power supplied by a single phase AC voltage of 220 volts 50 hertz for a domestic application. So what should be done first? What has to be done for, we need to calculate the value of current that is taken by, or power that is consumed by the load, right? We can use these methods. Here the intention of giving this problem is just to define how the values are considered, right? For a system where you have a AC, see the equation for power at the end, it is given something like this. Is it the same value which is already given, right? PAC is equal to 1000 minus 1000 to cos to omega t. So you can calculate the value of RMS value of voltage, current, or maximum value of current, right? When you are given with such type of examples. Let us, I think, no need of solving any problems for RMS and average value. Just get used to that, right? You just learn what are the values that can be calculated or taken, fine. And let us go for the next topic, that representation of vectors. And in the previous class, we were talking about some vectors where, how do you represent vectors in general? What's the need for representing a vector? Because all the time we can't write the value in terms
Because
of
AC is a vector quantity.
Yeah, because AC is a vector quantity, and we are not able to, or we are not possibly, we can't represent them all the time in terms of mathematical expressions. We need some other ways to produce it, or to illustrate it, or say it as present it for easy understanding of the learners, right? So whenever it comes for a vector, what is a vector in general? I already shown you a waveform where how it is shown as a sinusoidal yesterday. We took 45 degrees of angle, and for every 45 degrees we have shown like this, right? The same is shown here. From position 1 to 2, it is 45 degrees. From 2 to 3, 45 degrees. So this is the maximum peak it can, the vector shows. And already said that the vectors represent the length of this vector represents the magnitude of the quantity, and with respect to some reference, the angle deviation is known as phase, or phase difference, right? Now, how do we represent them? How can we represent such vectors? Is we can represent them in three forms. One is the polar form, another is rectangular, and third one is the exponential form. Let us discuss about one after the other. So first method of representation, you call it as a polar form. So in AC systems, when you solve the problems, I think you will be coming across this much. But according to your syllabus, we are not dealing much with these types of representation of AC. But somehow to have an idea or clear picture of vectors, we will discuss about this representation of in polar form, right? So what is a polar form representation? Is that polar form is where the length and the angle of its vector denote a complex number. Suppose if this is a vector, some vector you called as V, right? It is making an angle theta with some reference, and I call it as a reference. So how do you represent this vector now? Here is this vector V can be represented with two terms, that is a magnitude of vector at an angle of theta. That's it. Vector V, or if I want to make it a numerical, I call it as vector V1, can be represented with two elements. One is magnitude of the vector and angle at which it is suspended, or where it is positioned with respect to a reference. As simple as that, fine. So what does it indicate when, suppose if I have a equation for V2, vector V2 as 30 at an angle of minus 30 degrees. Let me write it as 60 degrees. So what does it indicate?
60 degrees below the reference.
So the a voltage vector V2 with a magnitude of 30 volts is suspended or is lagging a reference by minus 60 degrees. That's it, right? So I can draw it something like this. If this is a reference, this is, assume this to be 60 degrees. and this is V2, and I can represent this magnitude of V2 is equal to 30 volts. That's it. I think this will be better than representing that in terms of a waveform, right?
Yes, sir.
So representing the vector in terms of magnitude and phase angle is nothing but a polar form. In polar form, we will take the length, magnitude and phase angle, and it will be denoted by a complex number. Fine? Yeah. Let us go for the next one, where the second type of representation is, yeah, mismatch. Okay. Second type is a rectangular form. So what do you mean by rectangular form is that assume a axis just like this, real and imaginary axes, right? Suppose if I want to give a magnitude of this value 4 plus j3, what does it indicate? So in general, rectangular form of representation consists of, suppose I can write it as z is equal to a plus jb. Suppose some form of representation, right? Where a and b are some quotients and b is some value. Fine. So what is a and what is b? A is a real component and b is a imaginary, right? And suppose if I say, so how do you get to this value is that, suppose the same vector which you considered in the previous example, let me take the same thing. Suppose if this is the case, right? If this is the case, I will use the same example for representing in a rectangular form. So let me check, see here. So what was the expression that was considered? Yeah. So with respect to some reference, I have a vector which is making an angle of 60 degrees, which was given as this magnitude, V2 magnitude as 30 volts. So based on this, I can draw a axis like this, x-axis of the y-axis. So this, whatever that falls on this axis, you call as real components, and this as imaginary. So now I can split this into two parts here, 1 and 2, right? Suppose if this is some value x and this is some value of y. So how do I represent the vector v2 now? Vector v2 can be represented as x plus jy. As simple as that. Am I clear? So
Yes, sir.
instead of directly giving the magnitude, or instead of directly giving the exact value of the vector, we can indirectly give them in terms of other parameters in between. See, what does this parameter mean? In general, in a graph theory, how you write it in a graph, we'll give the coordinates here, right? Some let's say 4,0. Here we write it as 0,3. Usually, on a graph, how you write it, right?
Yes, sir. Ordered pair.
Yeah, we write it in an ordered pair here, where you call this as imaginary components as 0,3, and here it will be some 4,0, right? So we can represent. What does it indicate? What does it represent? That we will be having three coordinates here, just like this. So from origin 0,0, we have a vector which on x-axis it's 4 and on y-axis it's 3. So that is what we are doing it in the reverse here, that we can represent them in terms of real and imaginary parts like this. So where do you use these methods? Where do you use these types of representation? We use them in terms of in AC systems actually. In DC, we are talking about, in general, in fundamentally, we were talking about resistor, inductor, and capacitor from unit 1. But in DC circuits, we don't have L and C, right? Because we know that the properties, fundamental properties of inductor and capacitor, that inductor acts as a short circuit for DC and capacitor acts as a open circuit for DC. We heard that, right? We studied that, right? We had so now when it comes for DC, the impedance offered is only the resistance, or the opposition offered for the flow of DC current is only the resistance. But when it comes for AC, it also involves both inductor and capacitor, and the properties of inductors for AC and DC AC will definitely change. That is, the inductor opposes the sudden changes in current in a AC system, whereas capacitor doesn't allow sudden changes in voltage in AC system. So they have certain impact in the flow on the flow of current. So when you consider the resistance offered by the circuit parameters in a when you have using a AC system or AC supply, definitely not only the resistor, you will also have inductor and capacitor in affecting the flow of current, right? Affecting the performance of the system. So what should be done now? What can be done in general? When you write the equation for AC system in a DC system, what is the equation we write for V? Usually, what is the equation we write? It is I into R, right? But when it comes for a AC systems, it will be I into Z. What do you call this I into Z as? What is Z then?
Impedance.
Yeah, Z is termed as impedance. So now, if I have a impedance, right? So what are the components that comprise the impedance then?
Inductor, resistor, and capacitor.
Yeah, so the complete equation for a Z, okay, a complete equation for Z can be given as R plus J into XL minus,
XC.
yeah, XL minus XC is the equation which we can write for Z. What does it indicate then? What is XL? What is XC? We are aware of J, R, right? R is the resistance offered for the current to flow. What about XL and XC? What is?
Inductive reactance and capacitive reactance.
Yeah, we call them as, what is XL now? XL is the inductive reactance. And no doubt the units will be ohms. How can represent this reactance with ohms, right? Similarly, and what's the magnitude of this XL?
Omega L.
Yeah, 2 pi f L or omega L. Yeah, 2 pi f L or 2 pi or else omega L. Similarly, XC can be considered as capacitive reactance and represent with
1
ohms.
by omega C.
Yeah, represented by the units are ohms and the magnitude is represented by 1 by 2 pi fc, right? So this is what the difference between a AC circuit and a DC circuit. So when it comes for such elements, when we know that this is the final complete expression for Z, right? But somehow somehow the two values will not be present at once. Either it could be consisting of L or it could be consisting of XC, but not both at a time. Why it is not possible to have both at a time?
Sir, because if one is in steady state, the another one might get reduced from the circuit.
Similarly, CCC, what will happen in general is, suppose if this is a resistor and I have a inductor, I have a capacitor. For simplicity or for simplifying or writing it in simplified way, let me give you some values. R is equal to, I write it as 10 ohms. Let me write XL is equal to 20 ohms and XC is equal to 15 ohms. Substitute them in the equation for Z. What will be the value of Z? What will be the value of Z if I substitute those values? What happened?
10 minus 5J.
10 minus?
5J.
Yeah. What will happen to the other value?
Which one, sir?
XL minus XC. You don't find XL or both XL and XC there, right? The only thing we find either is XL minus XC or XC minus XL, but we find we will having only one term, right? For this equation, the value of Z can be written as 10 plus J 5. Suppose if I want to make this XL to be 25, what will be the equation now? Z is equal to 10 minus J5. Is that okay?
How, sir? We are considering XL as larger, no, sir.
Yeah, previously it was larger. In the second case, it is not larger. The XC is larger. Is that okay? I'm just considering two different
I thought
circuits.
that was XC. Okay, sir. Fine,
Yeah.
fine.
So in the first case, I'm considering XC is equal to 15. So what will be the equation? 10 plus J of 20 minus 15. You will get it as J5.
Yes, yes.
Now, when it is in terms of XC, if XC is greater than XL, what will happen to the value of Z? It will become 10 minus J5. So in an equation for Z, if the before J, if it is positive, the value is XL. If it is minus, the value is XC. Is that okay?
Yes, sir.
Yeah. Now, when you represent these type of terms, right? Impedance is one of the best example for vector representation. One is, so if I want to represent this in a polar form, I'm representing it as 10 plus J5. Okay. In the previous case, we talked about polar. How do you represent this then? If Z is equal to 10 plus J5 in rectangular form, what it will be in the polar form?
Sir, don't we use phasors for representing, sir?
Z is also phasor, right?
No, sir. Means we use phasor form of representation. Like XL is upwards and then XC is opposite.
That is how we come to the conclusion. How did I write this equation? How did we write this equation? We wrote the same equation here. This is R, this is XL, this is XC, right?
Yes, 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 sir. That.
Yeah. Yeah, we'll come back to this when we write the equations for pure inductor, pure capacitor. But
That comes under different categories, sir. Not in polar, not in rectangular.
which one? This?
Yes.
Yeah, this is representation of rectangle. That's what I said, right? Representation of vectors. This is all vectors, right? Suppose if I
Oh,
want to write it, how can I write the Z? I need to add it as R plus JXL, right?
yeah, yes, sir. Yes.
So I'm just writing them in the numerical form here. That's it. I just want to
Oh,
represent them, but I want to represent them in a simpler form.
okay,
So
sir.
if I write it as 10 plus J5, what does it indicate? On x-axis it's 10, on y-axis it's 5. So I get it as 10 plus J5 here. Isn't it? I can represent something like this, right?
Yes, yes, sir.
Yeah, I can write it as 10 plus J5. Okay. So now, if at all, this is a rectangular form of representation. And how do you represent them in a polar form? How do you represent them in a polar form?
We find angle by tan inverse of y by x, sir.
Hmm?
We have to find angle, no, sir.
Yeah, we need
In
to
polar.
find some angle, or else it's just like converting a rectangular form to polar, right?
Yes, sir. Yes.
So how do you get them is, how
First,
do you
we
get
take
the
the
value
magnitude.
magnitude of this? No doubt, when you write this vector here, Z, it should be written something like this: Z at an angle of theta. So what's the value of Z you are going to get here? What's the magnitude? How do you calculate the value of magnitude of Z? It's just like writing this as under root of 10 square plus 5 square.
Yes, sir.
That will give the magnitude, right?
Yes. 15, 15. We'll get 15, sir.
Will it? How?
15.
How?
100 plus 25, no, sir.
Yeah. What is under root 1 by 25? Under root 125. If it is, I think 625, if you get, it is 25, right? Okay. 100 plus 25. Under root 125, what's the value you are going to get? 5 into 5
Yes, sir.
into 5,
15
right?
only. 15 square, sir.
15 square is 125. Is it?
5 root 5.
Oh, sir. My bad. My bad. Sir. Sorry.
Yeah, it will be cubic, 5 cube, right?
225. It's sorry. Sorry.
Yeah, it's 5 root 5. What's the value?
11.18.
11.18 ohms, right? So you got the magnitude. How do you get the value of theta?
We can use tan inverse of y by x
Yeah,
cos.
same equation. You can take theta is equal to tan inverse of imaginary by real, right? So
Yes, sir.
5 by 10. So what's the value you are going to get here? Tan inverse of 1 by 2. 45? No.
$26.565
No. 26.565
degrees.
degrees. So I can represent the same Z here in terms of magnitude, that is 11.18 at an angle of 26.56 degrees. So this is how we represent them in the polar form. Is that okay?
Yes, sir.
Yeah, this is how you represent the vectors, and you have one more method to we can employ for representing the vectors, that is called as ellipse identity, where we can write the equation. I think this was copied here. So what's the equation I have here is this, right? What is the equation we can use is e power j theta is equal to cos theta plus j sin theta. So what's the equation I can write for representing is e power j theta, can write it as cos theta plus j sin theta. So this is how we can represent the value here. Suppose if at all I want to write it as z, right? Z vector z, I can write it as z into cos theta plus j sin theta. All representations are one and same, right? Am I clear with this? This is one of the representation, but mostly we use those two, polar and rectangular, for most of the cases. And we use polar form of representation for multiplication and division most of the times. Yeah. So for multiplication and division, I also write it as cross and divide, right? We use polar form. And where do you use this rectangular form? We use rectangular form for addition and subtraction. Is that okay?
Yes, sir.
Yeah. So now let us go for two definitions. One is form factor and one is peak factor. So what's the definition for a form factor?
VRMS by V average.
Yeah, the ratio of RMS value to average value is known as form factor. For a pure sinusoidal waveform, the value will remain it as 1.1. Right. So because we know that, how do you get to this conclusion 1.11? Here is the equation. See, we have the commonality between these two, right? What is that? What is the commonality between them?
We can convert it into I
Yeah.
naught in terms of I naught.
Yeah, RMS has can be, and average value can be written in terms of maximum values. So the ratio of IRMS by I average can be given as form factor. Right. Similarly, you also have something called as peak factor or crest factor, which is the ratio of maximum value to the RMS value. So definitely we know that maximum value will be more than that of RMS. So definitely the factor will be more than 1.1, that is, it will be equal to 1.414. Is that okay? These are the two factors which are generally used or mostly used for an AC system. What are they? RMS value and form factor and peak factor, right? So this is regarding the representation of vectors regarding form factor and peak factor, and I want to discuss about what happens whenever the current flows in a resistor, inductor, and a capacitor. I want you to solve this, right? And I will be giving a time for you to solve with them, right? I'll give the introduction how to calculate it. You just do them and upload in the group, right? So let me take a new slide here. Let me take a extra slide where I can. Yeah. So shall we solve it? Shall we derive the conditions for what happens when current flows through a pure resistor, pure inductor, and pure capacitor?
Yes, sir. But are these derivations are in syllabus, sir?
Yeah. They are not in syllabus exactly, but
Okay, sir. Means I was just asking because I
no,
would
no, no, no.
note down otherwise.
Yeah. I think it's better to note down because they may not give directly have in the syllabus, but they might ask you in some other form. Is it,
Okay, understood, sir. Means they may
yeah.
add it like derive this and then find out.
Yeah. So they want to you to prove. Sometimes they may ask you to prove whether what happens, what is the relation between voltage and current in a pure resistor, or prove that the current lags the voltage by 90 degrees in inductor, right? So we'll just go through it. It will not take more than 5 minutes. So you just follow as I say. That will be fine. Yeah. Now write it as, keep the heading as AC through pure resistor. I think we have solved this in the classroom itself. I can play the same PPT, but I think it will not be that effective when it comes for AC, right? So let me assume that I have a pure AC source and I have a resistor, pure resistor, right? And I have a current flowing here with some source. Let V is equal to Vm sin omega t, right? Therefore, what will be the value of I will be? I will be definitely be equal to V by R. So what is the equation you get for V? Is Vm sin omega t by R. So what is the equation will be? Vm by R sin omega t. So I can write I is equal to Im sin omega t. Right? So what is happening with the voltage waveform is that the waveform for voltage, a pure sinusoidal waveform for a voltage, let me write this as V, okay, and this as omega t 0, right? Since it's having 0 pi 2 pi, the current will also follow the same waveform, right? The current will also follow the same waveform, starting at same point and ending at the same point, right? With certain magnitude here, right? This will be the magnitude of I max. This is the magnitude of V max. And I can calculate the value of P for power. What's the equation I can write for power? V into I, right? We just now derived the equation. What is the equation we wrote? VRMS into IRMS. Did we derive this?
Yes, sir. Yes.
Yeah, we derived that PAC is equal to VRMS into IRMS, right? So what will happen when I have a waveform like this? See, suppose if this is uh, fundamentally if this is a voltage waveform, right? Let me draw it as a current waveform. Yeah. Suppose what what will be the value of power now? In simple sense, we can say that since voltage and current are positive, right? Definitely the power will remain positive, right? Isn't it? The magnitude of this is power, this is voltage, and this is current, right? Now, what will be happening in the second negative half cycle?
It will
Yes.
again remain positive, sir, because
It
both
will
are.
also again remain positive
Yes,
because
sir.
the value of voltage is negative, the value of current is also negative. So P is equal to minus V into minus I will also again become the positive value, right? Is that clear? So what happens when our current flows through a pure AC, pure resistor? What will happen when the current flows through a pure resistor? The power will be dissipated as heat energy, right? This amount of power, since it's positive in both the directions. What did we assume when it is a positive half cycle and a negative half cycle in general? When it is a AC waveform, what did we assume when that it is one is positive and one is negative? In a system where you have such type of uh, supply, we assume that during positive half cycle current flows from load to source, and the negative half cycle it flows in reverse, right? So, but we know that from this waveform we can clearly say that voltage during positive half cycle flows from positive source to load, and in the negative cycle it will flow from load to source. But what is happening to the power? Power is flowing in the positive direction all the time. There is all the time the power is spread from source to load. That's what it means, right? There is
Yes,
no
sir.
negative cycle. What does it indicate? All the
Power is
power is flowing
continually
only in one
being
direction.
dissipated.
And you know that what happens if you want to calculate the average value? Definitely the average value will be lying between this minimum and a maximum, right? So definitely the value of power will remain positive. Am I clear?
Yes, sir.
So the resistance, or you consider the load, is consuming the power continuously, and the average power is a positive value. Clear? Yeah.
Yes, sir.
Now let us go for a inductor then. AC, throw, and inductor. I call it as a pure inductor, right? Right. So assume that I have a same circuit, right? Same circuit where I have a pure inductor and I have a current flowing and voltage. And let V is equal to Vm sine omega t. And what is the equation I can write for I? What's the equation I write? What's the relation between voltage and current in inductor?
N phi by L.
Phi by L. Okay. After that, in terms of L, dV by dt.
L is equal to minus I dV by dt. Yes.
I is called L dV by dt, right?
Yes, sir.
Is that the equation derivation we found for inductor? We calculated the same, right? We found them. So now what will be the equation for this I? What's the equation for that? I is equal to, substitute the value of B in terms of here. So what's the equation you are going to get? d by, you write it as omega t because not the t is not a variable here. Omega t is a variable, so sine omega t. So what's the equation you are going to get here? L into I is equal
Sir,
to,
we will get VM also, no sir, VM.
yeah, sorry. Where is that Vm? I can pull it out, right? Can I take it out? LVM. Yeah, d by dt of sine omega t. So what is the equation you are going to get for is it v is equal to L di by dt or I is equal to L dB by dt?
1 minute, sir. I'm checking and I'll tell you.
Okay.
Equals to L di by dt.
V is equal to L.
di by dt, sir.
d5 by dt actually.
Yeah. So what will be the equation for I then? If it is V is equal to, or else V is equal to L di by dt, what is the equation for I then? We already have an equation for V, no need to find for that. So what will be the equation for I? 1 by L integral V dt. Is that okay?
Yes, sir.
Very
Yes,
first
sir,
classes
correct.
we have derived this, right?
Yes, sir. Correct only.
Yeah. Now you substitute the value of V here and get me the value of, sorry. This is 1 by L integral of Vm sine omega t dt. So get me the value for this I, equation for I now. Integrate that and get me the value for I, equation for I. Integral of sine
Minus
yeah.
Sir, we should take
minus
minus
cos
sign,
omega.
sir, there.
We should take minus.
Minus sign, sir, because when we integrate, we'll get minus cos. So that minus minus will be cancelled.
Suppose if you won't get minus, won't.
No, sir, because the equation is E is equal to minus L di by dt. So I think we have to consider in integration, sir.
Okay. Okay, you get it as minus. I'll write it here. I is equal to Bm by L cos minus cos omega t by omega, right?
Yes.
Vm by omega L, we want it as minus cos omega t. So what is the equation I can write for minus cos omega t? Can I write in terms of sine? Or can I directly write sine cos omega t in terms of sine? Can I write this in terms of sine omega t minus 90 is equal to cos omega t? Is that accepted?
Yes, sir.
Because suppose, yeah, suppose if we want to remove this minus, right? If you want to take it as minus L di by dt here, so the equation will become like this, minus of minus, it will become plus here. So we'll write it as Vm by omega L. This can be written as sine omega t minus 90 degrees. What's the need? Why we convert this cos to sine then? Because we want to find a relation. We should have a relation between voltage and current in terms of sine. Already we have omega voltage in terms of sine, so we definitely want the current to be in terms of sine. So convert that into sine, and whatever the value you get here, you just Yeah, that's what it becomes, right? Sin omega t minus 90 is equal to minus cos omega t. Then there is no need to use this minus sign here, right? Is that okay? Will you accept this minus sin omega t minus 90 is equal to cos omega t? Or I can write it in other way as well. Sin omega t minus 90 is equal to minus cos 90, cos omega t. Is that okay? Yeah, we can use it, right? So we have applied the Lenz law, but we haven't taken the consider the negative effect. So in general, we use the same equation, v is equal to dA by dt. So use the same here, right? And we are least bothered about this polarities in, yeah, rule number 15. What happened? We can we are least bothered about the polarities in the AC systems, right? So somehow we can write this value of current in terms of this as I is equal to I is equal to Vm by omega L sine omega t minus 90 degrees. So what is this omega? What is the value of what can I replace with this now? I can replace this with as Vm by, or else write it as Im.
XL.
Yeah, of course, this can be replaced with XL, no doubt, but I can write it as I maximum into sine omega t minus 90, where I can write I maximum is equal to Vm by omega L. Or else you write it as XL. Vm by XL, right? Is that clear? So now if I want to draw the waveform for this, if at all I want to draw the waveform for this, how do I draw the waveform now for voltage and current in a inductor? Suppose if this gives a voltage waveform, right? And I want to give you some current waveform. Okay. What will be the value of sorry. Yeah, forget about this. I just yeah. Let me draw the waveforms for these two. Let this be the voltage waveform. Okay. And what about the current waveform? Current lags the voltage by 90 degrees, right? So where do I start this waveform then? This is 90 degrees. This is also one of the 90 degrees, right? So where do I start this current now? Here in the position 1 or position 2?
Position 1.
Yeah, from here, right? So from here, so where it is, yeah, from here the current starts, that is after 90 degrees. Yeah, it will take up to 90 degrees. Now this waveform will be before 90 as well. So what is this equation? What is this waveform for? This is for voltage. This is for current. Now get me the value waveform for power then. What will be the waveform for power? I think we can divide them into 4 segments here, right? In section 1, this is section 2, this is section 3, this is section 4. Why do I divide them into sections here? What is the need for dividing them into sections here is, in the previous case, we considered that all the voltages and currents are starting at same point and ending at same point, but now the case is different. What is that? In section 1, both the voltage is positive, but the current is negative. So what will be the value of power? In section 1, what is the value of power given as? P is equal to V into minus I. Isn't it? So what will be the value of power? Positive or negative?
Negative.
So this, suppose if this is a power, the product of V and I am getting a power here, right? Is that okay? The power is negative because of this product. Okay. In second section, what is the equation for power now? V into I. It is positive, right? Both are positive, so V is also positive, right? Both V and I are positive, right? Is that
Yes,
okay?
sir.
Yeah. So now the power will be remaining, the product of V and I will remain positive, right? Now in section 3, it's same like section 1. The power, the current is now the current is positive, but the voltage is negative. So the power equation for power will become as P is equal to minus V into I. So we'll get it as negative. Similarly, in the third case, in the fourth case, what is happening in the fourth case? Both voltage and current are negative, right? So what will happen to the value of power? Power becomes positive. Is that okay? Is that clear? So what is happening now here? In the previous case, when we assume that you have a pure resistor, the power was flowing only in one direction. That is because we have a waveform only in positive cycle. The power was flowing only from source to load. Whereas here, what is happening here in this case? The current in the first segment or first section, it is negative. That means the power is flowing from load to source. In the second section, it is positive. What does it indicate? The power is flowing from source to load. Now in the third section, it is reversed. That is, power is flowing from load to source. And in the fourth section, it is positive. That is, power flows from source to load. So in all these cases, what's the average value now? In the previous case, where we assume the average value, it should be between these two. Because the minimum, what is the minimum point? Here is the 0, maximum value is the peak. So average will be between these two. What happens to the average power in this circuit now? Zero, right? Now, when you consider a pure inductor, what is the power that is consumed by a pure inductor now? What's the power that is consumed by a pure inductor? Is zero. Am I clear? That's the reason why we consider the value. The inductor stores energy, right? It will store the energy and it will dissipate back into the circuit, right? Thereby, you call it as the energy storage device. Of course, it stores energy only for finite amount of time, right? So this is how what happens when the current flows through a pure inductor. Is that okay? Yeah. Can someone solve me for the AC through pure capacitor now? Solve the equation for pure capacitor and upload it. Let me see. Are you trying?
Yes, sir.
Yeah. Try to solve it and let me know if you face any difficulty. It should be just like the slide, right? All the things in one page. What is the relation between voltage and current? What is the equation for current in a capacitor?
V equal to Q by C, sir. That is I by C.
I by C. Okay. But we derived some equations, already. We derived
Sir,
some
I
equations.
think we have to take charge.
Current in the capacitor, I'm getting I equal to I am
Yeah.
I think we have to
current.
take charge, sir. Q is equal to Q naught
So for the
sine
current, I'm
omega t.
getting I is for the current in capacitor, I'm getting in AC circuit I is equals to I am sine omega t plus pi by 2, where I am is equal to Vm by omega c.
Yeah, that's fine. That's good. So I just want see for inductors we derived it as I is equal to LDI by dt, right? Similarly, what's the equation you have relation between voltage and current in a capacitor? We derived it, right?
So,
I is equal to C dV by dt. Don't we have that equations which were derived in the first or second class? Haven't we derived that? Do you have that equation? I is called C dV by dt. Current is given as time rate change of voltage, right? In a capacitor. So we gave it as I is proportional to dV by dt. So C is taken as proportionality constant. So just what's the equation? What's the someone said the answer? What's the equation you got?
I is equals to I naught into sine of omega t plus pi by 2, sir.
Yeah, that's fine. I naught in the sense you're considering I naught as what's the
I
equation?
maximum, that is
Yeah.
V
Vm
naught
into
by
xc.
1.
No.
Vm into xc, sir.
Yeah, that's what I want. I naught can be considered as V naught or Vm into
xc
XC.
or omega c.
Yeah. So you get the same equation, approximately the same, but what will happen here? Instead of writing it as say this value, we are going to what is the equation you are going to get here? It is I is equal to Vm into omega c into sine omega t plus 90.
Current is leading the voltage, sir.
Yeah, this is what the equation you get, right? Where I can write this as I maximum, right? I is equal to I max sine omega t plus 90. Is that okay?
Yes,
Yes,
sir.
sir.
Yeah. So now you draw the same graph for that, similar graph for that. Draw the voltage and current waveforms and draw the power curves. Are you getting the similar graph? Definitely you will get the similar graph, right?
Current will be drawn from upwards, sir, in positive.
Yeah, similar in the sense,
First
not
one.
exactly the same, but okay, similar, right? That means the current will be leading, right? In this case, it will start from here. It will start from here, right? That means you'll be having a positive wave here. So now see here, for this waveform, the waveform in this circuit will be just like this, right? Suppose if this is the voltage, now where will be the current now? The negative cycle will start here. That means already the first half will be like this, right? Is that okay?
Yes, sir.
Now, when you draw the power, and this will be the first half, this will be the second half, this will be the third half, and this will be the fourth half, right? So in the first section, second, third, and fourth, right? So in the first section, both are positive, right? So the power will be positive. The negative cycle in the second half, what is happening? Voltage remains positive, current comes negative, right? So what will happen now? Power will become negative. In the third section, both will be negative, so the power becomes positive. And in the fourth section, current is positive, voltage is negative, so it will become negative. Is that okay? So what is the power consumed by a pure capacitor now? What is the power that is consumed by a pure capacitor? Average power. What is the average value now? Yeah, current always flows from source to load, but what is happening now here? We are assuming that positive in the sense positive power means power flowing from source to load. Negative power means current flowing from load load to source, back to source, right? So since the area under the curves, right? The area under these curves in the positive and negative directions are same, right? So the power consumed is power delivered. That is, whatever the power that flows from source to load is equal to the power that is flowing from load to source. So both are equal. So definitely the average power, P average, will be equal to 0, right? So the power consumed over a complete cycle, if the average power is equal to 0, the power consumed by a capacitor or a inductor or a pure inductor or a capacitor will be equal to 0. So out of R, L, C, resistor is the only element which consumes power, which has some definite value of average power, whereas R and C, the average power is equal to 0. Is that okay? Am I clear? Is that okay?
Yes, sir.
Yes, sir.
Shall we move on?
Yes, sir.
Okay, fine. So this is what happens when you represent them when current AC flows through a pure inductor, pure capacitor, or a pure resistor. Now, when we represent them on a on a polar form, right? Representation is also one of the important term, right? One of an important task for scalars. So when it comes for representation, right? I think vector. Let me take some reference here. Now, when it is a pure resistor, how do I represent the voltage and current? Voltage and current will be in phase, right? For resistor. Why? Because both are having the same equation, right? Vm sin omega t and Im sin omega t. V is equal to I is equal, right? So I can represent this as V, this as I. So how do I represent this equation? V is equal to Vm sin omega t and I is equal to Im sin omega t minus 90. Minus 90 is for inductor, right? So how do I represent them?
I will be downward, sir.
Yeah, this is V and exactly 90 degrees. Hope so. Assume that this is 90. Okay. And this is I. Right? Similarly, what happens to the capacitor now? This is V, where is I?
Upward.
Upward 90 degrees. Yeah, this is I. This is exactly 90 degrees. Right? This is I write it as IC, this is IL. So on a common platform, on a common reference, if I take this as V, I can draw this as IR, right? And I can write this as IC and I can write this as IL. Is that fine?
Yes, sir.
Suppose if I want to get this in terms of say a voltage in terms of voltage triangle, right? Suppose if I want to term it as a voltage triangle, do one thing, just multiply with R on the all sides, right? You multiply this IR into R here, multiply with IC into XC here, or multiply with IL into XL here. So if there is a triangle formed here, we call it as a voltage triangle. Suppose if this is a triangle formed, what is the values we can take here? Or else let me draw it like this, something like this. So what is the value here is VR. This is VC, right? This is exactly 90 degrees. So what do you call this as? A voltage triangle, right? Yeah, impedance triangle is what we form here, right? Before multiplying this C, before taking the values of IC, IR, XL, if suppose say if I take this as reference, what is the value I'm representing here when I take this as reference? If I take this as reference, right, I'm representing R on this axis. I'm representing XL here. I'm representing XC here. This is 90 degrees, 90 degrees. Is that okay? Now, if I join these two, what are the triangle that is formed? A, B, C. You call it as an impedance triangle. What do you call it as? Impedance triangle. Okay. So what do you mean by impedance triangle? The representation of all the terms R, XL, XC, right? What do you call it as? Impedance triangle. So now we can derive some equations from them as well. Now, if at all I want to draw the triangle for impedance triangle for the lowercase in the sense, what does it mean? For XL, this is XL, this is R, right? Right? So what do you call this as? The hypotenuse, you call it as Z. What is the equation I write for Z? R plus JXL. Similarly, what is the equation I write for this here? Sorry, for where is that triangle? Okay, let me draw here.
R minus JXL, sir.
Yeah, 1 second. Let this be the value here. So what's the equation I am going to write for this? This is XC. This is R, this is 90 degrees, and this is Z. What is the equation we are going to write here? R minus J X C. Yeah. This is how we write impedance triangles, right? Next, what we are interested in also writing the voltage triangle, right? What is the voltage triangle I said here? Yeah. Suppose if I multiply with relative impedance terms on to this current axis, then you form a voltage triangle, right? In these equations or else in this representation, if I have an angle here, suppose say if some I have some angle here, suppose say if this is for a pure resistor and inductor, right? Suppose what happens if there is some value of inductor, which a practical inductor where I have a source and I have a inductor with some internal resistance. We know that every coil has its own internal resistance, right? After all, what is a coil? What is an inductor? It is just a wound conductor, right? The conductor is wound into form as an inductor. So definitely there will be some internal resistance for that inductor, right? So if it is not a pure inductor, if it is having some internal resistance, right? So what will be the value of that such lagging current? It will not be purely 90 degrees. So it may something lie between 0 and 90, right? So this is a value of theta or pi which we calculate, right? And this is a value of XL, this is the value of R, right? So when I want to calculate this value, I call it as Z. Then I call it as Z because how do I calculate this value magnitude of Z now? Because why I'm writing it as Z? Because it's the sum of R and XL, and we know that what is the representation we give for Z? Z is equal to R plus JXL, right? XL will give the value of exact the pure inductor, and what is the R is the internal resistance. So how do I represent them on a graph like this, which you call it as RX diagram? What do you call it as RX diagram? What is the what do you plot on this graph here? You represent this R in, and what you represent on y axis, you represent the value of XL. So now summation of these two or intersection of these two will give the value of Z, and this angle you call it as theta. So what is the equation I am going to write for this Z is R plus JXL, and the magnitude is calculated as said previous, right? We have done the calculation in previous for that magnitude of Z. What is the equation we wrote? Under root of R in plus XL square, or I'll say XL. This is the magnitude which we follow, right? That means if I have no if there practically if the pure inductors are not possible or if they are not available, instead of getting 90 degrees, we get certain angle here, right? So if I draw a triangle, impedance triangle for this, what is the equation? What is the triangle? How the triangle will be? Okay, 1 second. I will draw it here. One second. So I can draw it as R here, XL here, and this as Z, or else this is R, this is XL, this is Z, right? Why I'm taking it as Z? This length will be equal to this length, right? So that's the reason why I take it as XL. So whatever the angle I have here, let it be theta or pi. What's the equation I can write for theta in terms of what say Pythagoras theorem? What do you call it as? Sine equation and cos equation, I think.
Cos theta is equal to R by Z.
Yeah, I can write it as cos theta is equal to R by Z and sin theta. But we can write it as opposite by hypotenuse, right? What is the opposite I have? X by Z, right? So we can employ these type of equations when when we have some combination of R and L. That is, I can call this as series RL circuit, right? What do you call this as? Series RL circuit. So similar thing can be applied for series RC circuit as well. What happens if this is a RC circuit? Instead of coming to the bottom lagging, it comes to leading. That's it. Isn't it? Current leads the voltage. So instead of getting a lagging angle, you get a leading angle. That's it. So when you have a pure resistor, inductor, capacitor, the equations are very much valid. But when it is a pure, it's a combination of R and L or a combination of R and C, right? In different proportions. Suppose if R and L are equal, the magnitudes are equal, definitely the angle will be 45 degrees. But I'm talking about any value of any relation of value between resistor and inductor, you call it as a series RL circuit, right? And if it is between R and C, that is pure resistor and some resistor and a capacitor, you call it as a pure series RC circuit. So in such cases, the value will not be exactly 90 degrees. So what has to be done now? What should be done? We have to calculate the value of theta in terms of sin theta, cos theta, and based on the values of real and imaginary parts, right? That is how you calculate the values, right? So in out of this, what is the thing we have to what we want to study, learn more is about Z. So what is happening with the Z now? What is Z? What is in here?
Impedance, sir.
Yeah, impedance. Now give me a second. Fine. Now it's impedance. Fine. Z is equal to R plus JX is one type of representation, and you also have another type of representation in complex systems. What is that? Y is equal to G plus JB, or J. To be specific, it will be JBL. So what is this Y then? We studied Z is equal to R plus JXL, which is impedance is equal to resistance plus
Susceptance.
J of XL. What is that? Inductive reactance, right? Then what is this term? Y is equal to G plus JB. What is Y now?
Susceptance, sir.
Susceptance is this. Impedance, reciprocal of impedance. What is Y now? Y is reciprocal of Z. And what is Z? Is the reciprocal of R. And what is BL? Reciprocal of XL. We can even represent them in two forms, right? Suppose if it is, say, where do you use these? Let me give the clarity of these terms, right? So when it is, you call this as impedance, this is called as admittance. What is that? Y is called as admittance, is the reciprocal of impedance. Is that okay? And what is Z?
Conductance.
Is the reciprocal of resistance. And what is BL? Susceptance is the reciprocal of reactance. Suppose if I say this as inductive reactance, you call this as inductive susceptance, because you also have one more capacitive susceptance, right? Is that okay? But where do you use this? Where do you want to use this? Where do you use impedance representation? Where do you use admittance? See, impedances are used for series circuits. And where do you use this admittance? Parallel circuits, right? So what is the best example here is, suppose say Suppose if at all, if it is a series circuit, when I have a two resistors in series, what do you write this for? R1, R2, R3. What is the equivalent you write? R equivalent you write it as R1 plus R2 plus R3. Similarly, when you have them in parallel, right? If I write in terms of R1, R2, R3, it's a big task to represent. So if I write it as G1, G2, G3, right? What's the G equivalent will be? G1 plus G2 plus G3. No doubt G is equal to 1 by R, right? I can represent the same thing when you write it for R equivalent. What's the R equivalent? 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Doesn't matter, right? But when it comes for calculation, this becomes more simpler than compared to this. So the concept of impedance and admittance, right? What is the difference between those two? We use one for analyzing a series circuits and other for the parallel circuits. Am I clear with this? I think this will be enough for your fundamentals of AC circuits in unit 1. Do you have any doubts in the single phase AC systems? Please let me know. If not, we'll go for next topic. Are you okay with the fundamentals of AC circuits? Okay, that's fine, right? Okay, I thought of showing you, sharing you some MATLAB simulations for. I've heard software such as MATLAB, MATLAB, MATLAB. Where did you hear that? MATLAB 49? Yeah, is the screen visible?
Yes, sir.
Okay, designing and stuff, right? Okay, fine. So I have taken a simple circuit of KVL. Fine. See here, I have a circuit here where I can define these values as, instead of writing R1, R2, R3, I can give the values here. 1000. This as 500. I can give as 1500. So this is a handy software where you can simulate basic ideas of theorems, right? So see, you can display the values here where, see the we have given a, is it visible? Is the screen visible here? The voltage. Are these things visible?
Yes, sir.
Yeah. So I took a source of 9 volts and I connected resistors of 1000. It's struck on Thevenin's window. For everyone. Okay. Now, what do you see? No. It's the same. Okay. I think I need to stop this share. Okay, I will share it again. Okay. Is that okay now? Okay, fine. See, this is a simple set of series circuit, right, which we were deriving in the classes, right, for defining KVL. So assume a voltage source here of a magnitude 9 volts, and assume some 3 resistors connected in uh, series, 1000 ohms. This is the value of resistor, which can be seen here, right? A resistor of 1500 and 1500 in series. Now, once I run this, you can see the values. What does it indicate? Is the voltage drop across this 1000 ohms, 500 ohms, and 1500 ohms. You can easily change the value. See, if at all you want to change, you can change this to be 100. Okay, and you can run it and see whether it changes accordingly or not. You can do the calculations and you can find whether verify them, right? So if it will be better if you take some example which you already solved, right? Can someone share me an example of mesh analysis which you already solved, which you already have the answers with 3 loops? WhatsApp me the picture of the circuit which you solved. Let us define, or let us check, verify whether we can find those values or not. Someone sharing me? Do you have any circuit for mesh analysis? So I'm not able to. Did you send any circuit? Do you have any circuit which you solved for mesh analysis previously? Are you able to see this waveform, these values?
Yes, sir.
Yeah. Can I have a circuit which you already solved? I think you use some 3 meshes problem, right? Yeah. Did we solve this, which I got here? Okay. Then let us take this to solve this as, okay. So also group post that in the group. Let them see which problem we are solving. Find the network for the network shown, find the values of currents, mesh currents I1, I2, I3, right? Okay, so I think no need of these voltages. Okay, let them be aside. Even they are not required, let them be aside. Okay, this is also the third one. So we want to find the mesh current. So where is that mesh we want to find is here, right? So this will be fine, right? Okay. And what's the third one? 1, 2, 3, and this is the third one, right? Okay. So okay. So I want to display here. I want to display here. One, two. Okay. Fine. So what's the magnitudes of this voltage? It's 50. And what's the resistance here? 6 ohms. This is 5 ohms. And what is this? 18 ohms. This has 4 ohms. What is the last resistance? Is it 4? Four ohms, okay. So what's the current you got? I3, you are going to get it as 0.5. I2, you are going to get as 1. I1, you are going to get as 5. Was it the currents that you got? Did you solve it? Yeah. So the currents are okay, right? So we can change them, we can tune them according to the values which you want, right? And we can get the values of power, voltage, current, whatnot, everything, right? So this is just a simulator where you can dump your circuit and get the values, right? I think you can access them. You can access this. What do you say? MATLAB online through your institute mail ID. You can register that for and use that for first 1 month, free for a 1 month course, right? Or you can use them in your in our laboratory, BW laboratory as well, right? So this is how we calculate it, and we also have we can do them for nodal analysis. We can do it for whatnot, for everything, right? So this is one sort of software that is available for solving the problems, right, or for finding the answers directly. And I thought of making you to write the lab manuals directly, right? What is going on with the other lab, other BW laboratories? CR, you have any information about BW lab for the other sections? What they are doing? Does anyone have information regarding that? CR, Heman? Number 12. Is there anyone talking about BW labs from other section? No response. Yeah. Sierra, Ananya, what's going on with the lab, BW lab for others, other sections? Do you have any information? Are they uploading their worksheets, lab worksheets? Yeah, try to learn from your friends whether what they are doing for that, right? So what you didn't get? I didn't get mission nodal. Mission nodal, what's topic or worksheets?
Sir,
Yeah.
for the workshop though, they asked us to upload. If our worksheets are corrected, we can upload them in our CMS. If
Okay.
not yet corrected, then after the offline college starts, then we have to get them corrected.
But I haven't for BW we haven't got any chance for getting it corrected, right?
No, sir, you corrected a few.
Only very few.
Yeah.
Yeah. Then what about others? You can upload only once you get them corrected, right?
Yes, sir.
So let it be. Let us see what happens after from the next week. So by next week, I think we will be having offline. Hope so. Let us see what will happen. If the condition still persists the same, then we will upload the worksheets which you already written, and I will give the marks online directly.
Okay, sir.
Okay, we will be starting about the rest of the part in Unit 2, right? That is network mesh analysis and network theory in the next class. Fine. So that's all for today. If you have any doubts, you can ask me. CR, post the attendance. Send me the attendance. I will update it in the CMS. Okay.
Okay, sir.
Fine. Any more doubts?
Sir, don't end this meeting. I'm taking note.
Okay. Take it now.